Go.
Hi, I'm Saran Rangarajan,
I'm Nicole Griebel.
I'm Mike Partenio.
I'm Ali Maradia.
and we're group B42 in EECS 203, and our topic is direct proofs.
Okay, so today we're going to be talking about direct proofs, and we're going to be showing you guys how to do a direct proof of a statement. So first we're going to talk about the type of statement that you'll be given in order to do a direct proof of. So the type of statement you're going to be given is going to be in the form P implies Q. So an example of this is, if today is Saturday, then we wash the car. So in this example, P is going to be today is Saturday, because that's the first part of the statement. And then your Q, which is the second part, is going to be we wash the car. Okay, so we're going to use a truth table to show that we're going to use a truth table to figure out when this statement could be false. So, truth tables, you have to go through each example. And false, false. Okay. Okay. So, if we're given P and Q are both true, then we're going to have a statement, if today is Saturday, then we wash the car. So this is our given statement, so this is obviously going to be true. And then the next example is going to be when P is true and Q is false. So that one's going to be, if today is Saturday, then we don't wash the car. So this is obviously does not go along with our original statement, because if today is Saturday, we're supposed to wash the car no matter what. So since this doesn't go along with our original statement, then we know that this one is false. So the next example is a little tricky. So we have, if today is not Saturday, then we wash the car. So this one's also going to be true because our statement does not say that we can only wash the car on Saturdays. So we could wash the car on a different day, so say it's Tuesday, then today is not Saturday, but we do wash the car. So that makes this statement true. And then the last statement is going to be, if today is not Saturday, then we don't wash the car. Now since the original statement says only on Saturdays do we have to wash the car, then the last false false is going to be true as well. So an important thing to recognize is when you have a statement P implies Q, that the only way for that statement to be false is when you have P is true and Q is false. Now this is really important for direct proofs because direct proofs recognizes this and uses it to prove the entire statement to be true or false. So now we're going to get more specific into direct proofs and talk about the definition of what a direct proof actually is. So I'm going to give you guys the definition of a direct proof is going to be a direct proof of a statement in the form P implies Q, just like our last example, is done by assuming P is true and using rules of inference. We'll get more into those as we go through our examples, to show that Q is true for all cases. Okay, so the reason that a direct proof works is that, let's go through step by step. So we have a direct proof of a statement in the form P implies Q. So we're given P implies Q, just like our if today is Saturday, then we wash the car. And then we do this is done by assuming P is true. So we're going to say that P, in a direct proof sense, we're going to say, we're doing a direct proof of this statement. Then when we would say that P is true, and then we would use rules of inference to show that Q is true for all cases. So in the last example, we would go through step by step and show that the only way it would be false is that if today is Saturday and we didn't wash the car. So since we know that P is true, because that was the assumed case, and we're showing that Q is true, this can be done because we know that the only case where this would be false is if we had true implies false. So by showing that when P is true, that Q has to be true, then we eliminate the possibility for Q to be false, which is right here. So if we eliminate that possibility, we only have true implies true, which we know then would prove that our statement all around is going to be true. So this is how you would do a direct proof. Now we're going to go into some examples in order to show it a lot better. We're going to start with some easier examples and then get a little bit progressively harder. And we're going to go right into that now.
Alright, so example 1 is just a simple example of a direct proof, and by definition we know that if n is an odd integer, then n is equal to 2k plus 1, k being any integer. So we need to prove that if n is an odd integer, then n squared will be odd as well. So we can start by squaring both sides of the original equation, which will give us n squared is equal to the quantity of 2k plus 1 squared. And we can then rewrite that as n squared is equal to 2k plus 1 times 2k plus 1. And if you FOIL that out, then that is equal to 4k squared plus 4k plus 1. Now we can simplify that into n squared is equal to 2 times the quantity of 2k squared plus 2k plus 1. Now, if we look at this, we know that because k is an integer, this whole quantity right here will also be an integer. So we can actually just replace that with basically any other variable just as another integer. So let's say x. So if we rewrite this, we now have n squared is equal to 2 times x plus 1. Now if we look at the original equation for just n, we have n is equal to 2k plus 1. And as you can see, they are exactly the same, apart from the fact that we have a different variable for the integer x instead of k. So by direct proof, we have proved that n squared is also an odd integer if n is an odd integer.
And now we'll do a more difficult example. We're going to prove that the following logical statement is always true. So we have not P and P or Q implies Q. And so we're going to show that if we assume that the left part of the statement is true, then that means the right part of the statement must always be true. And so since we have the AND operator, in order for the whole expression to be true, both of the parts must also be true. So that means not P must be true, and P or Q must also be true. So in order for not P to be true, that just means that P must be false. And if we take that to our other expression, now we have false or Q. In order for this expression to be true, we must have Q being true, because in order for an expression with the OR operator to be true, one or both of the parts must be true. And after that, since now we have Q must be true, coincidentally this is the same thing that is on the right side of our logical expression. So basically we've shown that if the left side of our logical expression is true, no matter what, the right side must always also be true as well.
Okay, for our final example, it's going to be a little bit more difficult. It's going to be the quantity P or Q and the quantity P implies R and the quantity Q implies R, and that whole thing implies R. So from our last example, we learned that since we have the AND symbols right here and right here, that all of these statements have to be true in order to make this entire side true. And as a direct proof, we want this entire side to be true so that we can imply that this side is true as well. So for each of those statements to be true, we have P or Q must be true, and we have P implies R must be true, and we have Q implies R must be true. So if P or Q must be true, then that means either P is true or Q is true for this entire statement to be true. So we're going to start with assuming that P is true. If P is true, then we come to our second statement. Then we have true implies R equals true. For this statement to be true, then R must be true, which shows that our final statement up here is also true, which would be the end of our proof. But since we assume that P was true, we have to go back and assume that if Q was true in this statement. So if Q is true, then we have true on this final statement implies R, which equals true. And if true implies R equals true, then we know that R must also be true. So since we showed that if either P or Q is true, R must be true, then we know that this part up here must be true no matter what. So then we proved by direct proof that if this side of our if the left side of our statement is true, then the right side of our statement must also be true. Thank you
very much
for watching our video.
Go
Blue!